All right, this is Mr. Sindel. I'm recording a video way too late. I just started at 12:40 at midnight, and I have to go camping tomorrow, and I haven't done any lesson plans for the Yosemite trip, so I'm like really nervous. Anyway, welcome seventh graders to Wednesday's lesson. So today is all about reviewing procedures, how to add, subtract, how to multiply, and we'll throw off dividing until tomorrow on Thursday. But before I get into procedure, I need to give a warning. Don't get bogged down in procedure. Don't think that procedure is the end all be all. Oh, Mr. Sindel said I just have to walk the number line. You have to be careful because too often I see students that memorize the procedure, but they don't see the bigger picture, and it causes them to make mistakes into the future. And to illustrate that point, I'm going to read you a story that I read, wow, in 2015. Man, that makes me feel old. 7 years ago. It's titled, Are You a Dishwashing Robot? And it's talking to you, the student. And this is written from a high school teacher that is 1 year older than myself. He's been teaching for 7 years now. He is an excellent teacher, but he does, his official title is Math with Bad Drawings because he's not very good at drawing like I am, and he likes math like I do. So we have a lot in common. I think he teaches on the East Coast, though. So I'm going to read to you. You're just going to sit there and watch, right? This is part 3 of a 4-part series on how to avoid thinking in math class. The other ones are hilarious as well, and I would love to read them to you guys one day. If you found this super boring, though, then tell me you don't want to do it. All right, here we go. On Friday, I realized yet again that my too clever for their own good students were finding ways to answer questions without understanding the ideas. And that strikes fear into my heart, like, oh no. Rather than reckon with the concept of slope, they were just memorizing a complex rule. And here's the rule that they memorized. Slope is the coefficient of the x. But then they have this weird star in the top right. Except if there's a coefficient on the y, then you have to divide by that. But unless there's a y and an x on the same side of the equation, then multiply by -1 first. But that assumes that there aren't multiple x terms, in which case, ... you'd have to combine like terms and do a bunch of other things. Notice that this is a procedure. If you just follow this procedure, you will eventually get the correct answer. But notice that it started off with a simple, elegant statement. Slope is the coefficient of the x, and it got more and more complex once you start unraveling what you really have to do for a variety of problems. So let's read on. That's all true so far as it goes, but it's as opaque and sinister as the tax code. Math is supposed to make sense, I told them, and in my flailing to explain why, I found myself reaching for my favorite rhetorical tool, the overly detailed analogy. So, weird advertisement. So, to see what math class is like for memorization-driven students, imagine that you are a household robot, and I'm talking to you, the student. This is you. You are now a robot, and your job as a robot is to clean dishes. Now, you don't know anything about food, meals, or human culinary practices. You're a robot after all. All you know is what you're told, and your only wish in life is to follow your instructions and to carry out the right procedures. You can already see where I'm going with this. You're going to only do procedures, and hopefully you'll see how silly this can be. You're thrilled when a nice family takes you home, teaches you how to recognize dishes as dirty, clean, and dry. And then you get your simple rules to obey. Look how simple these are. Clean the dirty dishes. Leave the clean dishes to dry. Stack the dry dishes in the cupboards. It's nice, easy, simple instructions. Ah, nice. Of course, you don't know what dishes are for. Are they for decoration, for sport? You don't know how they get dirty. Are you careless? Did you drop them on the floor and they picked up some dirt? You don't know the point of cleaning them. Don't they keep getting dirty? And you don't know why they belong in the cupboards afterwards. They're hidden when clean and displayed when dirty, maybe? I don't know. You just know that there are those 3 steps. That's the procedure. And you follow those steps. You're a good robot. And there's this picture. Clean the dirty, dry the clean, stack the dry. Clean the dirty, dry the clean, stack the dry. Clean the dirty, dry the clean, stack the dry. And this is you, the student, of course. You're just repeating the same procedure over and over to solve your math problem over and over without really understanding how to do the math problem. All right, on your first day, you notice some dry dishes out on the table. You start stacking them in a cupboard, just like you've been told. When your owner starts screaming, "What are you doing, you dumb machine? I just set the table a minute ago." You're confused. You, the robot, you're confused. Weren't you just following the rules that said stack the dry dishes? Look at that table. Those are dry dishes. They're on a table. I was told stack dry dishes. Go back up to those rules. Like, what is it? Yeah, it says stack the dry dishes. That's rule number 3 in the cupboard. I see dry dishes down there. I stack them. So the owner has to amend the instructions. Look at rule number 3 now. So stack the dry dishes in the cupboards, asterisk, except in the hour before a meal. In that case, leave them because they're just setting the table, right? So they're just adding more to the procedure. Okay, weird and contradictory, but whatever. Okay, one exception isn't so hard to learn. A little later, you notice the plate's getting dirty. There's all kind of lumpy organic stuff piling up on them. So you grab them and start cleaning. "No," you hear, "stupid robot. That was our lasagna." What's all this lasagna talk? Isn't the organic dirt on the dishes? Aren't dirty dishes supposed to be clean? Isn't that like the entire job that I'm supposed to be doing? And soon your first rule is amended as well, just like the third. So now our first rule says, clean the dirty dishes, but wait until all the large dirt particles are gone. Wait until the food things are gone. But you don't know what food is. You don't have the bigger picture. You're just following a simple procedure, right? Wait until the large dirt particles are gone? How paradoxical. You're supposed to focus your cleaning on the less dirty dishes. Waiting for the really dirty dishes to magically clean themselves halfway? Like, that doesn't make any sense because, again, the robot doesn't know that you're going to be eating food off the dishes and it makes them a little bit cleaner, right? All right, well, no matter. Strange and inconsistent rules are still rules, and being a good robot, you follow the rules. But the next day, they're yelling at you again. "Why didn't you clean that plate? You left it out overnight." You look at it. It's still got tons of dirt, lots and lots of dirt on it. Didn't they say not to clean it if it's got such big particles left? A moment later, you're programmed with a new first rule. Clean the dirty dishes, but wait until all the large dirt particles are gone, or until removal of particles is stopped, right? If you stop eating, then you have to clean that off. So just amend the new procedure. You're starting to get anxious now as a robot. I don't know if you have feelings, but you are getting anxious. What once seemed a simple scheme of rules has grown rather complicated. You could really use some encouragement for your efforts, and so you leap at the first chance to put this newly modified rule into action. The removal of particles on one dish has stopped, so you begin to clean it. But no, only more shouting. "I was just pausing to take a sip of water. I wasn't done." And a new, even more complicated rule. All right, rule number 1. Clean the dirty dishes, but wait until all the large dirt particles are gone, or until removal of particles has stopped for at least 5 minutes. Rule number 2 has been amended as well. As you can see, leave the clean dishes to dry unless it's right before a meal and there aren't enough dishes, in which case manually dry them. And rule number 3 has been heavily amended. Oh my God, look at this. Stack the dry dishes in the cupboards, except in the, not hour, but 45 minutes before the meal. In that case, leave them, but that's assuming they're on the table, and an addendum to that, or the counter. Those ones in the drying rack can go. Oh my God, look at all those exceptions. Look at this gigantic procedure. It all seems cruelly arbitrary. This once straightforward task, clean the dirty dishes, has become a nightmare, a cobweb of exceptions and contradictions in which you must calibrate your behaviors so precisely based on a bizarre condition and inscrutable requirements. I mean, look at those conditions. That's insane. Ladies and gentlemen, welcome to math class. Again, look at how the students are doing it. It started out with that simple rule. Slope is the coefficient of the x. except there's a coefficient on the y, then divide by that. Unless there's a y and an x on the same side of the equation, then you have to multiply by -1 first. And that's assuming that you don't have multiple x terms. Like, look at that. It's the same thing with a robot. What's missing, of course, is the crucial understanding of what it's all for. Why were you doing it? It turns out that you can't succeed as a dishwasher until you understand why dishes get dirty in the first place. The point of dishes, the robot needs to be told, is to hold humans' food while they eat it. When they're done eating, that's when the dishes need to be cleaned. Now there's a purpose. Now there's an understanding. You have the bigger picture. Now that you have the bigger picture, you don't need a complicated set of criteria. It makes sense. And the robot says, oh, I finally get it. Every rule, whoa, jumped up there. Every rule, even the craziest, most arbitrary mandate, has a reason rooted in an essential purpose. Why leave the dishes with big particles? Because the person is still eating. I understand it now. And so it is in math class. If you understand slope, not as the list of steps I'm supposed to follow, but as a rate of change, things start making more sense. Why is the ratio of the coefficients? Because look at what happens when x is increased by 1. Everything else goes up by 1 as well, or by whatever the coefficient is. You get to work a lot less, and you get to think a lot more. And that's probably the most powerful line of this entire article. If you understand the bigger picture, if you understand the essential purpose, the reason that you're doing what you're doing, you get to work a lot less and think a lot more. So powerful. All right. Now, conceptual understanding alone isn't enough. And any more than procedures alone are enough. You must connect the two, tracing how the rules emerge from the concepts. Only then can you learn to apply procedures flexibly and to anticipate exceptions. Only then will you get to the pat on the back that every robot craves. And he goes on to talk about what he did with his class. And he's really good at writing, and it sounds like maybe he's very humble, but it sounds like he garbled through the whole analogy. So that's, I don't think there's very much more of that article. Yeah, that's the end. So just make sure that when I'm talking about procedure, the takeaway here is don't just memorize the procedure. You're going to be that robot that's having a list of exceptions and you're not going to be able to remember them all. Remember the bigger picture of what we're trying to do with every single thing that we're doing in this math class for the rest of your lives. That's how you have to think about math. I don't know how long I've been recording. Does it tell me here? No, it doesn't. But I would like to also note that these notes are available daily on the Levi High School website, and I'll be posting them. There will be a permanent static link. It won't change. That's what static means. A static link on Google Classroom, and you just click on that, and it will open up this notebook. It syncs every 30 seconds automatically, so I don't have to do anything. It's kind of hands-off. All right, there are a simple set of procedures that you do have to know. And I feel bad for not being able to explain the bigger picture because I'm a new 7th grade teacher. I wish I had a better understanding of why we do the things we do. I can explain it at the higher level because it uses the shadow dimension, but you guys don't know about that yet, which makes things hard. So here are the things that we generally know. When we are adding and subtracting, this is all kind of review at this point. Adding and subtracting. All you're trying to do is you're supposed to count. The whole goal here is to count. The bigger picture, how do we count? And there are a bunch of rules and procedures associated with it, but you can do kind of, I think there's 3 methods. I've taught one of them pretty well, walking the number line. There's also Cody's method where he just has some procedures to memorize. I think there's only like 3, so it's not that bad. And there's a third one using counters, which is even more basic, but it takes a lot longer, where you have like, I think I can explain it really quickly, where you have like positives, positive tiles, positive tiles, positive tiles, and you have like negative tiles, and you're like, okay, well, this problem represents 3, and then I have a -2, and you can say, well, the positive and negative, they blow each other up like matter and antimatter, and this one blows each other up, matter and antimatter. The only thing remaining is a 1, so the answer here is just a 1. That's another way of showing how to add and subtract using tiles. There's my way, where you use the number line, where if I do the same problem, 3 plus -2, you say you're going to start on the number line at 3. So I'm going to quickly do a number line. Say I have 0, 1, 2, and 3. And this tells you the direction face. Direction to face. So there's the positive direction over here, there's the negative direction over here. So in my story, I'm currently a stick figure standing here at 3. I'm going to look which way? I'm going to look to the right. So I'm going to draw my eyes to the right, and there maybe I have a big nose or something. It looks like a tongue. I don't know, whatever. I'm looking that direction, guys. And finally, this last number here represents steps. And then if you're a positive, you're going forward. And if you're a negative, you're going backward. And that's everything. Like that, there's no complicated, I mean, that is the procedure, which is maybe complicated. But everything can be solved just using that simple thing over and over again. So in my example, I start here at 3, I face the right, I face the positive direction, and I'm going to walk 2 steps backwards, because negative is backwards. So I'm going to go backwards, and I end at 1, which is again the same answer that you get using the tiles. And then I'm going to patent this Cody's method. I'm even going to write it down in the notes. Everyone will refer to this as Cody's method. And it is purely procedural. And I am scared of purely procedural things, as you can clearly tell by the giant article that I just read to you guys. Cody's method is this. There are a series of conditions. So condition 1, you can have the same sign. And I'm already messing up his procedure. His procedure states that you have to have, step number 1 should be only one sign in between. So step number 1 says, like, if you have a problem like I just had up there, 3 plus -2, 3 plus -2, that has 2 signs in between, which means it doesn't satisfy that. So in order to do that, you're going to take these 2 numbers, these 2 operations, and you multiply them. And you have to know your multiplication tables of positive times a negative is a negative, and then you can now change this problem into 3 and a -1. The negative is overpowering. But again, you have other rules, like, let me give you a slightly different problem. What if I had 3 minus -1? This is a whole separate problem. I apologize if this is confusing. Maybe I'll choose different numbers so it's not confusing. So there's a whole separate problem. So 7 minus -3. Well, again, you have 2 operations, and it doesn't satisfy your first procedural condition of you can only have 1 sign in between. And some people say, when negatives kiss, it becomes a positive. Or you can think of it the other way, that if you multiply a negative times a negative, it's equal to a positive, because we multiplied here. And I'll write down the cuter one underneath here. 2 negatives kiss and become positive. And that's kind of the only options that you'll have. You can have like I guess I'm trying to think of another example that I might have where I have 2 signs in between. You might have like I don't want to use a 3. Let's do like 4 minus a positive 5, and this is the same case where you multiply these 2 numbers, and these 2 operations, and you say multiply. A negative times a positive is negative, so you just treat this as 4 minus 5. Either way, step number 1, you can only have 1 sign in between numbers. That's step 1. Okay, step 2, what do we have? Step number 2 is to do one of 2 things. You have 2 options here, option A and option B. Option A is if they have the same sign. If they have the same side, you're going to add the numbers. And the other possibility is they have different signs. They have opposite signs, which means you're going to subtract. So in this case, if I have, I'm running out of room here. As a quick example, if I have like a -3 plus 2, notice that these, I keep using 3. Let me make up some random. -11 plus 5. Notice that I have one sign in between, so I satisfied step 1. It has one sign in between, but now check out the sign. I have a negative and a positive. Well, those are opposite signs, which means I'm going to subtract. And here's the cool thing, the cool little condition about subtract, which is one of my favorite things to tell whenever you're doing this procedure. Ignore signs from here on out. So what that means is it doesn't matter. Like, you can treat this as this can turn into a problem like 11 minus 5. You can swap the signs however you like, as long as you have you remember what the original problem was. So don't change the original problem, rewrite it somewhere else, and you can do whatever you want. 11 minus 5 is much easier to do than -11 plus 5. So rewrite it however you'd like and ignore the signs. So 11 minus 5 is now 6. So that's 6. And then finally you get to step 3. So step number 3, hold on, you guys are in the way. Move, oop, you guys move over there. Step number 3 is to take the sign of the larger number. And if I come back to my original, this problem over here, you can see, okay, the original problem, the 11 was bigger than the 5. And the 11 had a negative sign, which means my final answer down here should be a -6. With those 3 steps over and over again, you can solve every single problem that you could have solved just walking the number line. But some people like the procedure. I'm just gonna warn you guys, again, be wary of the procedure. However, I'm gonna start using it here and there to let you guys be comfortable with it. So I want to do a few practice problems where I'm not going to do tiles, it just takes forever. I'm going to do a few walking the number line, a few of Cody's method, and then I'm going to review rules of multiplication, and we'll call it a day. And I'm not going to record a video for Thursday because it's 1 in the morning and I need to go to sleep. Friday is going to be a pattern task that you guys are going to be doing with the 8th graders, and I'm going to do a separate video recording for that in a little bit, which means I'm going to go to bed at like 4 in the morning. Dear God. All right. Examples. So walking the number line, and again, this is still review, so I'm guessing a lot of people are going to skip right through this. What if I have -3 minus -2? Let's go ahead and use Cody's method. I want to try it out. So step number 1 is I can only have one sign, so negatives kiss and they become positive, so it's going to turn into -3 plus 2. Okay, step number 2 is to check if they have opposite or same signs. So check it out. I have opposite signs, which means I'm going to subtract. So I can ignore the signs now and say it's going to be 3 minus 2, and that's going to turn into 1. And then step number 3 is to take the sign of the larger. And this is the original problem, kind of. I did modify this to this, but that's okay. Or sorry, this to this. But I'm still, essentially, I haven't done anything. I haven't dropped the signs and ignored the signs. Before I ignored the signs, the 3 was the biggest, and it had a negative, so my answer is going to be -1, and I box it. So once you know the procedure, it does go pretty fast. And just I'll do one final example for a number line. Wait, and let me do one more Cody's method, where, because I've done two opposite sign ones. So let's do like a -3 plus a -5. So in this case, step number 1, again, you can only have one sign in between, so a negative, sorry, let me write this down. Positive times a negative is a negative, so this is going to be a -3 minus a 5. Okay, now, they're both going in the same direction, a minus and a minus. They're both in the same direction, which means if they're both the same sign here, then you're going to add them, and you're going to say, okay, step number 2, if I add them together, I get 8. And again, you can ignore signs at this point. Did I say you're allowed to ignore signs? Ignore signs. Should be here, and it should be here as well. Just ignore signs. And then finally, in step number 3, you're going to take the sign of the larger. You always take the sign of the larger. Well, the larger is 5. Oop, I meant to do highlighter tool. Is 5, and it had a negative in front of it. So this is going to turn into a -8. And final answer, box it. So you've seen some variety in Cody's method. That was example number, I can say example number 2. And now I can do a number line example. Example number 3, a number line example. If I have, I don't know, have I done one with a ton of negatives? I have. Let's do like a 3 minus 10. Sure, why not? 3 minus 10. So the way that the number line works is you start here at, there's 0, 1, 2, 3. I'm going to start here at 3. So you can do a point, you can draw a human. I like drawing a human because I always visualize myself walking the number line when I'm doing these problems. I start at 3, so this is my start. And then which direction do I face? Do I face the positive direction or the negative direction? And if you remember my procedure, this sign tells you where to face, and I'm going to face that direction. So I'm going to face to the left. So I'm going to draw a face on my character. There's the smile, there's the eye. You can clearly see, maybe I can have some long, fancy hair right here. I'm clearly facing the left. And then I have to decide this number right here, is it a positive or a negative? Well, there's no negative in front of it, so it's a positive number, which means I'm going to walk forward 10 units. So if I walk forward 10 units, I'm going to walk 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm clearly in the more negative area, and if I count these out, I have negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, and negative 7, and you're kind of seeing why this one has a simpler procedure, but it does take longer if you can't visualize what's going on with this number line and you have to label it. Then Cody's method is a little bit more fast and efficient, which is why I encourage high schoolers to start adopting that sort of procedure. 7th and 8th graders, and sometimes freshmen, I still tell them to try the walking the number line. Our final answer was -7 for what it's worth. We should maybe box that. -7 is the final answer. All right, and before I get out of here, last thing, multiplying. I'm not doing dividing yet, but it's basically the same rules. Multiplying positive and negative numbers. There's just a set of criteria. There's not a good rationale. Remember, I always want to be thinking about the why, so I'm not that dumb robot that's just following a procedure. But I've only been taught the procedure, and I'm not sure what the why is for this one, so I'm not a very good teacher in this case. I'm apologizing to all of you. There's 4 rules that you need to know, and you just got to memorize them. A positive times a positive, I do a little dot for a multiplication sign, is a positive. A negative times a negative equals a positive. There's a way to summarize this at the very end, but I'm just writing them all out for now. A positive times a negative equals a negative, and a negative times a positive equals a negative. Generally speaking, if there's one copy, or I'll say one of each, then it will be a negative. And if you have the other case, same sign, if they're the same sign, it's always going to be positive. That's the more generic way to simplify those 2 rules. And giving you 2 examples before I can finally end this video. Didn't I say I was going to end this video like a long time ago? I forgot what example I'm on, but I'm going to do example 1 again. Example number 1. -3 times -8. Well, it's a negative times a negative. Look, negative times a negative. If I have both the same sign, if I have the same sign, it's going to be a positive. And it is indeed this rule right there. It's going to be a positive. And then I don't really write the plus sign. I just drop it. So 3 times 8 is 24. Final answer. And one other example. Example number 2. Let's do -2 times 3 times -7. Sure, why not? Now I have a bunch of things happening here. So the first thing that I'm going to do, PEMDAS isn't going to help us because everything is multiplication, multiplication, multiplication. So generally when you're doing multiplication, you go left to right, although it doesn't matter if it's multiplication right to left, left to right, it's going to be the same answer. So I'm going to start with these 2 first, and then at the very end I'm going to do the -7. The way that I'd like you guys to show your work is the way that I show my work. I'm going to first do these 2 numbers and say, okay, a negative times a positive is a negative. I know that rule. 2 times 3 is a 6. And then I'm going to bring down this number and rewrite the whole problem, -7. And then I'm going to come down and combine these 2. A negative times a negative is a positive. I don't write the plus sign because you don't need it. And then 6 times 7 is 42, so the final answer is 42. Noticing, I would like you to notice that I am boxing my work. Whew, that is it for today. I apologize for the super long video. I'm just making sure you guys have a good foundation of what I'm expecting from you. I don't want you to just memorize procedures. Sometimes you do need to do that for the more basic stuff, like today, multiplying. Thanks for watching. You guys have some checking your understanding work that if you have nothing else to do, you should just be doing in class. And then I think if you finish that, then you can just do independent reading. Tomorrow's going to be more of the same review. I'm hoping to get IXL set up, and people can be doing that hopefully today or tomorrow. Definitely not Friday. Friday should be more of a fun day and a pattern task. Thanks for watching. The next time I'm going to see you in a video is on Friday when we launch the pattern task. Thanks for watching. Bye.